Hello there, my fellow students. Not fellow, you're students, I'm a teacher, whatever. Today, we're gonna be looking at a statistical test called the ANOVA. So ANOVAs are used to compare the data from different groups against each other to see if there's any difference between the means of those groups. And as an example, we have a set of data here of seeds that have grown to plants of different heights, and we've grouped them by the radiation dose here from 0 to 40,000 sieverts. And you see the numbers in here, those represent the heights of those different groups. Now, you may be familiar with the t-test. There's another video about the t-test. The t-test compares two different groups against each other. The benefit of the ANOVA is that it can compare many groups at once. So it's basically repeated t-tests. One can say that in a broad generalization. It doesn't take into account the numerical relationship between these different groups, that it's 0 to 500 here and 0 to 1500 here. That doesn't matter. It just treats them as different groups. So we're not looking at the kind of the exact relationship. You're just asking ourselves, are there any differences between the values of these different groups against each other? And importantly, the type of ANOVA we're going to look at now, that is what we could call a global test. Means that it looks at all of these 5 groups as one to find if there's any difference between any two groups. You can follow then up the ANOVA with individual t-tests between the different groups to find if there's any, between which of these groups there is a difference. So the ANOVA that we're going to do now would report a significant result or significant different result if there's a difference between any of the groups in here. So that's a downside in doing it in Excel. I'm going to show you another example or another kind of program that will do it and do the same thing, but also make all the individual comparisons against each other. But okay, let's see how to do this then. So as in Excel, we have to have the analysis tool packs installed, and there's another video about that if you don't have that installed yet. But anyways, if we're going to do the test, we go to data, make sure that the data is clicked here, so the toolbar changes. And if you have the analysis tool pack installed, you will find this button up here, data analysis. Note that I have this in Swedish now, so sorry. And if you click that, you get these groups of data or different tests you can use. At the top, we have the one-factor ANOVA. And that's the one we're going to use now. It's called also the one-way ANOVA. If I click OK on that, I'll get a box like this, a prompt to give the in data. So here we can select all the cells that have the data that we're looking for. And these are the data from the 5 different groups. I'm going to press OK. And then it's going to ask if I want to group by columns. And in this case, yes, I do. These columns represent the different groups that I'm interested in. And then so the p-value that I'm looking for, and you can also, if I would have selected the top rows here as well, I would click this one to show that I have labels on the first row, and then I select where I want my results in just an area in this sheet, or if I want a new sheet or a new file, I'm gonna select new sheet. Then I press OK. And the output here tells us for each of these 5 columns, it tells us the number of data points, 0 in the last one, and the sum of the values, the mean, and the variance. The variance is just the standard deviation squared. And then it gives us a p-value here for the F statistic, and this is the value you were looking to get up above, and here's our specific F value. Maybe that's a bit above our level. But anyways, the p-value is what we're looking for. So this is 0.0000 and then 3.319 whatever. So it's much less than 0.05. So by convention, this suggests that there's there's a statistical significance between one of the groups at least. So at least between one of the groups. But here we want to also find if the other way of looking at between which of the 5 groups do we find this difference. So that could be a follow-up type of test we want to do. So there is a web page called statpages.info/ANOVA1sm.html. Here we can give the summary data to the different groups, and it would, we can, this web page will calculate it for us. Let's see if it likes the fact that we don't have any data in the final one, but I'm gonna minimize this and maybe make this one smaller as well so I can see everything at the same time. And then sheet 3, mean 98.4. This one is 69. Wait, 69.5. This one was 42.4. This one was 24.4. And let's see if we can give it the variance instead. Nope. So then we need to calculate the standard deviation equals std.abs wep, and then we can put those values as well. 19. Oh my god, what a silly goose. Just do this so I see them all at the same time. I don't have to look again. 98.4. I might have to put 98.4 instead. Sorry, it takes a few seconds, but I'm sure it will be worth it. So then we have 19.19, 19.59, 13.18, 6.5 actually. Okay. Boom. Boom. Let's see. Okay, so here, so this is what we call a post hoc test, and so basically a follow-up. Now, let's see. We can call this group 1 instead. So, compute. So then we get all the different p-values. You see that group 1 is then significantly different. Here we have the different p-values for each one. So basically, these ones are significantly different from each other because the p-value is less than 0.05. And group 2 is significantly different from all the other ones. Group 3 and 4 are not significantly different from each other, but 3 and 5 are, and 4 and 5 are not. 4 and 5 are not. That's interesting. I guess then it would be, yeah. So anyways, you can use that instead of doing the t-test. Let's see if the t-tests, it's a different test, so the Tukey test, I think. So let's see if we get a similar result if we would take, for example, group 1 versus group 2, just for the hell of it. And then we get a p-value of 0.02. So actually that's very similar. So yeah, exactly similar. So this suggests that this one is actually doing the exact same thing. So this is the Tukey test, post hoc test here is basically the same as a t-test in this case. So it's up to you if you want to do this, if you think this is faster instead of doing all the individual comparisons afterwards. As we see, that would be total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different tests. Anyone smart in math would be able to tell you that already from the beginning. But anyways, that's how to do the ANOVA. You follow it up with another test. And there's another test another way to follow this up as well. So if you want to be really thorough, you start with the one-way ANOVA to see if there's any difference between any groups. And if you don't find any difference there, that might suggest that your data doesn't have any differences. You can follow that up with this two-key or post-hoc test, or with a t-test. And then finally, another way of following it up, if these the different doses or the different groups, that the values here actually represent something that you're interested in, or you're interested in if the difference between 1500 and 5000 has any meaning compared to between 0 and 1500. So then we would look for a linear regression test or a correlation test. And there are two we can look for here. I tend to use the regression test because that also gives us a formula or an equation as well, the equation we're looking for. So let's see, the y data is what it asks for first. We give it the means, and then it will ask for the x data. That would be the radiation doses in this case. So the values are independent variable. So let's see what we get then. So this one gives us a non-working p-value. Is that because we have only 4 data points with values in? Let's just change this to 1 and see what it would happen then. I think that's the reason. Yes. No. That's interesting. It's because we have the data organized differently. So let's do it this way. 69, 42.4, 24.4, 0. And then we select these ones: 0, 500, 1500, 5000, and 40,000. So now let's do this properly. So the y data is organized like this. Yeah, I can't see that, and the x data here. Look at that. Now we actually get it. So yeah, for the regression test, you have to organize them in 2 columns like that. So here we have a p-value. Actually, suggests that we don't have a linear relationship between them. And of course, you can look at them like that and see in the actual graph. That's always a good idea. And you see they don't really follow a linear relationship. They actually follow some other relationship. Now, if you want to be really cool with this one, of course, you would see that that's some kind of logarithmic relationship. So you can convert these ones into their natural logarithms. Of course, that will not work. Well, we can perhaps set that one to, just set it to 1 for now. And then we can do the data analysis. The y data is the same, but these ones are different. Then it would actually be significant, of course. So if you go to this one now and do then you see that they're actually following linear relationship. That's also a little bit above maybe our pay grade. But anyways, that's how we can follow up the ANOVA. But ANOVA is a good way to start when you have many groups of data with raw data inside them, to see if there's any difference between the different groups. So that was all about the ANOVA. Please give some comments if there's something you want me to explain further. Have a good day.